Hi scholars, I hope that you and your family and loved ones are doing well. We at SEO are thinking about you every day, we care about you, and we're sending our best wishes. So usually in an SEO math class, we all rely heavily on your knowledge, your thoughts, and the ideas that you bring into the classroom. And there are many opportunities for you to talk with your classmates about an idea or to come to the board, to share what you're thinking, to ask questions, and just in general to solve problems together. And so although much of these activities aren't possible when you're watching a video, I still encourage you to try to watch this video as if you were in a classroom actively. And so what this means is to take out your workbook or a notebook while we go through the lesson together and take notes in it, just as if you were in a classroom. Feel free to pause, rewind, and watch parts of the video a second time if you're confused. And make a note of things that you're still confused about after this lesson so that you can ask your instructor. All right, sounds good. So let's get to it. A couple lessons ago, we talked about this idea of closure. So for example, we said that the natural numbers were closed under addition because if I took one natural number, for example 3, I took another natural number 5, I added them, I would end up with another natural number, right? So this is this idea of closure, that if I have one of a kind of a number, another kind of number, I'm going to end up with the same kind of number when I do this operation, in this case addition. We saw that although the natural numbers were closed under addition, they were not closed under subtraction, right? And so the reason why was because if I take my same two natural numbers, instead of adding them, if I subtract them, I end up with, right? This is natural number, this is natural number, but I end up with, what is this, -2, right? What the heck is that? That's not a natural number. It's not a counting number, right? So we said that although they were closed under addition, they were not closed under subtraction. And this, in fact, allowed us to build or to create a new type of number. If we recall, we said we can extend the natural number system to include integers, right? So this allowed us to expand our number system, right? We first started off with all the counting numbers, 1, 2, 3. And all of those numbers, we said these are all natural numbers. And then we said, well, actually, because when we add subtraction, we end up with these new kinds of numbers. Let's go backwards, right? We can have negative numbers, -1, -2, -3, so forth and so on. And if we take all this whole big bucket of numbers all together, we can call those integers, right? So this is where natural numbers are sort of nested inside of integers. Okay, so this is just a quick reminder so we can get to our think, pair, share for today, which is, are integers closed under division? Okay, well that's an interesting question, so take a minute to think about it. And the answer is no, right? So this question is asking us, if I take any two integers, right, and I divide them, will I always end up with another integer? So again, integers could be negative numbers, they could be 0, fine. They could be positive numbers, but they're whole numbers, right? Whole numbers, they could be negative or positive. So, for example, if I do 12 divided by 5, right? Do I get, another way I can write this is 12 over 5, right? Is that number an integer? And the answer is no, it's not, right? I could write it as a decimal, as 2.4, or I could write it as a mixed fraction, right? We did this, I'm sure, in middle school. But in either case, this is a new kind of a number, right? And so we're able to use an operation and pre-existing numbers that we had. We're able to use division on integers to again expand the number system to include rational numbers, okay? And so this lesson, we're gonna be all about rational numbers. Okay, let's keep going. So in general, rational numbers or fractions can be a little tricky because there are often multiple ways to interpret the same fraction, okay? So we're gonna take a quick look at 3 different ways of understanding or interpreting fractions. So the first way that you likely have seen in school is using a part-whole model. And we can see what a part-whole model looks like, right? So if I want to interpret the fraction 2/10, it means take a whole thing, like a pizza, cut it up into 10 pieces and take 2 of those pieces, right? This is the 2 here, this piece right here and this piece right here. Those 2 pieces are a part of the whole pie. And so there are a couple benefits to this, right? So we can easily use a part-whole comparison to make sense of percentages, and we're going to do that a lot during semester 3 in the algebra unit. So for example, we can say, oh, 20% of the circle is shaded, right? Because I can rewrite this fraction 2/10 as 20 over 100, and this is basically what it means when we're talking about percents. It's how much out of 100, right? It's a part-whole relationship where the whole is 100. That's why 100% equals one whole thing. Another benefit of this model is that we can sort of make sense of proportions, right? So for example, we can see if I said, look at these 2 pies right here, this one right here and this one right here, which one has more shaded area, right? You'd say that's exactly the same because 2 out of 10 in the top one is the same thing as 1 out of 5, right? It's the identical area, and in fact the proportion 2/10 does, or 2/10 equals 1/5. This right here is a proportion, which is an equation that says that 2 ratios are equal to each other. You could cross multiply if you wanted to verify that this proportion was indeed true. So this is actually true, right? And so we can have sort of a nice area model to look at it, and we can also use what we know about proportions. So one limitation of this model is that we're not able to sort of make sense of or draw a picture of dividing a quantity by a fraction, right? So what would, for example, what would 1 divided by 1/5 mean, right? Well, if we want to interpret it as this part-whole model, it would mean take one something, right? One circle, right? This does not mean divide it into 5 parts and take 1/5 of it. No, it means divide it into 1/5 of a part, right? I mean, I could divide it into 2 parts. That's easy, right? I could divide it into 4 parts. I could divide it into 1 part by just leaving it alone. But what does it mean to divide it into less than 1 part, right? In fact, the fraction 1 over 1/5, that actually equals 5, right? And so we're going to talk about that a little later. So how can I start with 1 circle and sort of divide it up in some way and shade something and end up with 5, right? It's really hard to sort of conceptualize that, to imagine that. So that's one limitation of this model. So the limitation, it doesn't mean that it's terrible, we should never use it. It just means that some models, they have their benefits and they have their limitations. So this model, it does have some benefits for us in these two situations, but it sort of breaks down when we want to divide by a fraction. Okay, let's keep going. So our next common model is called the partitive, or we can also call it the sharing model, and this is interpreting fractions, rational numbers, as sharing, right? So for example, if I want to interpret what is 10 divided by 5, or 10 over 5, what does this fraction mean, right? One way to interpret it is I start with 10 apples, there they are, and I want to share them, right? This is why it's called the sharing model. I want to share them equally among 5 friends, right? Well, okay, everyone gets 2 apples, right? Because there's one friend, there's another friend, so forth and so on, right? And so that's why the fraction 10 over 5, we can also interpret it as a division problem, 10 divided by 5. That's why I can say that that does equal 2. That's how I can interpret it in the sharing model. Everyone gets 2 apples, okay? This is probably the first way that we talked, or that we learned about division in elementary school. And so the benefit of this model is that we can make sense of the connection between multiplication and division. It's sort of very visual, right? So 10 divided by 5 is 2, and I could also interpret that as saying that if I have, right, 5 groups of 2 apples each, altogether I have 10 apples. And so, right, these two equations are really, they're saying the same thing. They're talking about the same thing. Again, the limitation with this model is that we can't divide by a fraction, right? So if I had 10 apples, right, if I want to try to use this model, 10 apples, and I want to share them with half of a friend, right? How many apples does each friend get? What does that mean? What is half of a friend, right? It's very confusing. It doesn't really work, so the model sort of breaks down. So let's take a look at one more model that is really powerful and that is going to play a role in lots of higher level mathematics, not even higher level mathematics, but even this idea of slope, right? We're going to talk about slope over the summer. And the measuring model, this is the one we're talking about right now, is really, really powerful way to interpret slope. So in the measuring model, the fraction 10 over 2, right, means that we want to measure 10, could be 10 feet or 10 meters or whatever. Here's a length of 10. We want to measure it, right? We want to measure our 10 units and with a ruler that has a length of 2 of these units, right? And so the question that 10 over 2 is asking is, how many rulers is it going to take if the rulers are 2 feet? How many 2 feet rulers will it take to measure 10 feet, right? And there it is, right? It's right there for you. It's 5 rulers, right? So I can take, this is my 2 feet, so there's 2, 4, right? 6, 8, 10. Okay. So I can measure my length using this ruler, okay? Now the big benefit of this model, as opposed to other models, is that it does not have the same limitation as the other 2 models have. Okay, so if we recall, the big issue with the other models was, what does it mean to divide by a fraction, right? That sort of does make sense. I don't have half of a friend. I can't divide a pizza into 1/5 of a part. And so this model really allows us to deal with fractions. So let's take a look and see if we can sketch a picture to interpret and then calculate what these values are. 10 divided by 1/2. Right? And 1 divided by 1/5. Okay, so let's start real quick. Using this measuring model, 10 divided by 1/2 says that I have a length of 10, let's just call it feet, okay? I have a length of 10 feet, and my ruler, right? So again, here we're interpreting the numerator in this fraction as a length, and the denominator, we're interpreting it as a ruler. And the actual fraction, we interpret that as how many rulers would it take to measure this length. So if I have a 10-foot length and my ruler, here we'll just use a different color for the ruler. Let's say my ruler is, we said, what is it, 1/2 of a foot? So there's my ruler. So it's a small ruler. And let's say, okay, so how many 1/2 of a feet does it take to measure this 10 feet? Well, if I had 2 of these rulers, right, that would get me up to 1 foot, right? Well, we can use sort of proportional reasoning. That means if I had 4 rulers, that would get me up to 2 feet. 6 rulers would get me 3 feet, and we can keep going, and we can see that it would actually take me 20 rulers to get to 10 feet. And I'll be darned if 10 divided by 1/2 doesn't equal 20. It does, right? So this is correct. So we're able to use this idea of rulers and lengths and measuring in order to make sense of this otherwise strange division problem where we're dividing by a fraction. Let's just do another quick example. 1 divided by 1/5, what would it look like? Well, here's my length. Let's make it a meter this time. Let's say this is the length of 1 meter. And let's say that I have my ruler is, the length is going to be 1/5 of a meter, right? That's the length of my ruler. How many 1/5 would it take to get to 1, right? Well, 1, 2, 3, 4, and 5, right? Because 1/5 times 5 will get me all the way back to 1. So 1 divided by 1/5 equals 5. So again, this is 5 rulers. And I just want to highlight that in this particular example, we see a more general pattern. So we can say that in general, whenever I have a situation where I have 1 divided by 1 over x, where x is any number, the answer is just x. So you can try that out with another number for x if you like. Okay, let's keep going. Example number 2. So Santa has a ribbon that is 4/6 of a yard long. So let's draw that ribbon, and we're going to say that this is 4/6 of a yard. And here it is. Okay, so if she cuts the ribbon into equal pieces, each measuring 1/6 of a yard, how many pieces will she have? So this question is really asking, how many 1/6 are there in 4/6, right? And so we can reason with that sort of just in our minds and say, oh, there must be 4 of them. Or we can sort of draw it out, right, and say that if that's 1/6, right, so there's 1/6, there's 1/6, and there's 1/6, and here's 1/6, that there are indeed 4 of them, right? Okay, so if we wanted to interpret this as a fraction or a division problem, right, this would be 4/6 divided by 1/6, right? And I could have also written this, right, as 4/6 divided by 1/6 like this. I could have written it that way. In general, when we get into algebra, we don't really use, in the same way that we don't use the x sign to mean multiplication, right? We also don't really use our division sign as much. I mean, it is used, but in general, we can also just interpret it using this fraction bar. So this fraction bar right here was what we mean when we are trying to divide. So 4/6 divided by 1/6, and we said that that was equal to, well, what was it equal to? It was equal to 1, 2, 3, 4, right? So this is sort of using the measuring model. So this all equals 4. And notice, I just want to highlight or draw your attention to the fact that this is a 4 divided by 1. And 4 divided by 1 equals 4 as well. So notice that the sixths here, although they play a role in the problem, right, because we're still dealing with the same type of a unit, in this case sixths of a yard, we really don't have to pay too much attention to them, right? So in general, if I have, for example, here, I have a fraction like a divided by c, so this is, we're going to try to generalize things, right? All of that divided by b, okay, divided by c, so b over c, right? Say, what does that equal? And in general, that's just going to equal a over b, which is exactly what we found here, where 4, where is really just 4 over 1, right? Those are the same things. So this right here is sort of a general rule, and it's always nice whenever you see a pattern and you say, huh, look at that pattern, right? It's nice to say, well, is that pattern, is that always true? And then you can sort of play around with it and say, oh, it is always true, right? In this case, the c doesn't really play a role in the final result. And so we can sort of say that in general, we can come up with a generalization that can help us solve other problems. Okay, let's keep going. So this think, pair, share is asking us to compare the relative sizes of two fractions and to answer the question, which fraction is bigger, which one is larger? So let's use the measuring model. So again, the measuring model allows us to interpret a fraction a over b. We're going to interpret our numerator a as a length, our denominator b as a ruler, and the fraction a over b is really asking us how many rulers would it take to measure this length? How many b's would it take to measure a? Okay, so let's use this sort of lens to see if we can, without doing any math, just using our reasoning to see which fraction is bigger. Okay, so in this case, notice that we're asked to compare 4/7 or 4/5. I'm going to write them bigger over here, 4/7 over here and 4/5 over here. Using our model, the length that we're measuring is the same for each of them, right? But the ruler is larger for 4/7. So this is a larger ruler, right? And this one is a smaller ruler, okay? So the question is, if you had a larger ruler, would it take you more times or fewer times to measure the same length? Okay, so let's just draw a picture of that real quick. That's sort of a complicated question. So here's our length of 4, okay? So if I have a ruler that's small and I have a ruler that's larger, right? Would it take more of the small ruler or more of the large ruler to measure this length, right? And the answer would take more of the small ruler, right? Because the small ruler is smaller, so you'd have to have more of them to measure this length, right? So that means that, if we want to go back to here, one way that we can reason about which fraction is larger, right, is we can say this fraction is larger this one is larger or bigger because the ruler is smaller. A smaller ruler means you need more of those rulers to measure the same length. Okay, so that's one way to reason about that. Let's take a look at B. So B is asking us to compare 10/4 and 9/4. So in this case, we say we have the same ruler size, right? The ruler size is 4 in both those cases. The only difference in here is the length, right? So if I'm using the same ruler, but I have a larger length, right? So here, this is talking about the 10 there. This is a larger length than the 9, which is smaller. Well, then clearly, this 10/4 right here, this one is going to be larger, okay, because the ruler size is the same. So I'm using the same units, I guess, right, to compare the magnitudes of the denominator. So that's great. So here we have that 10/4 is larger, so that's fine just by comparing here our numerators. And C, let's see what's going on. So here we're being asked to compare 4/10 and 5/13. And using our ruler model over here, we're kind of stuck, right? Because we don't have the same lengths, right? 4 is not 5. We also don't have the same ruler sizes. 10 is not 13, right? So in this case, if we want to compare the relative sizes of these two fractions, we're going to have to find a common denominator. So in this case, our common denominator is going to be 130. So 4/10, I'm going to rewrite that, right? So I'm going to have my 4 and my 10 over here, and I'm just going to multiply by 13 and 13. Okay, and all this together, 4 times 13 is 52 over 130. So that's what I end up with. So 4/10 equals 52 over 130. So that is a correct way of rewriting 4/10. And then we're going to take 5/13, and I'm going to rewrite 5/13 again, 5/13, and multiply top and bottom by 10. I'm going to use parentheses here to represent multiplication. I could use a dot as well. Either one is correct. And all together here, we're going to end up with a 50 130ths. And notice that now that I have the same size ruler, right? That's what finding a common denominator is. It's really another way of finding the same ruler. Now, because they're the same, just like in example B when they were the same, I can compare the relative magnitudes of just the denominator and see that, 52 is bigger than 50, since 52 is larger than 50. 4/10 is greater than 5/13. And you can check that on your calculator. Okay, let's keep going. So now that we have a couple of ways of interpreting fractions, let's see how we can operate with fractions. So think, pair, share. What is 2/3 of 15? So when you see that word of, we want to interpret it as multiplication. So this question is asking us to multiply 2/3 and 15. So 2/3 times 15. And we could do this in a couple of different ways, still get the same answer. So one is to, if I interpret 15 as 15 over 1, right, I can rewrite this as 2 times 15 all over 3, or over 3 times 1, right? Again, we can sort of multiply across. This is one way of operating with fractions. And I can rewrite this as 30 over 3, which is otherwise known as 10. So 2/3 of 15 is 10, right? I could also rewrite 2/3 of 15. I could also rewrite that as 2 times 15 over 3, right? This is the thirds part. There's the 15, and here's my 2. And 2 times 15 over 3, well, 15 over 3 is just 5. And again, we're going to end up with 10. So any way you slice it, any way you sort of manipulate this multiplication problem, we're going to end up with the same answer, 10. In general, how do I multiply with fractions? If I have a over b times, I'll just use parentheses here, times c over d, where a, b, c, and d are just any old numbers, we can just multiply straight across ac over bd. So this is in general how we multiply fractions. And in example 3, we see another way of interpreting this algorithm, right, of how to sort of in general multiply fractions. And we can actually use an area model to interpret it as well. So for example, if I wanted to find what is 1/4 of 2/3, right, one way to do it is we start with our whole thing, right? In this case, it's a nice rectangle, that's fine. I start with 2/3 of it, so there's 1/3, and there's another third, right? And I'm being asked, what's 1/4 of just this part that I shaded? Well, in order to calculate 1/4 of just that part, I want to divide it into, right, 4 parts, if I want to use it the part-whole model, and I want to find out what is just one of those 4 parts, right? And so this right here is this picture right here. So 1/4 of, right, the 1/4 is the red, of 2/3, which is the blue here that we shaded, right? 1/4 of 2/3 is just this area right here, right? This area right here. And this area right here is, well, I have 12 rectangles and there's 2 of them. So the answer is 2/12, which I could also write as 1/6. So this is one way of using an area model to interpret multiplication of fractions. Let's keep going. Example number 4. If 3/7 k is equal to 12, then what is the value of k? So I'm just going to rewrite this over here. So I have 3/7 times k is equal to 12. How can we solve for k? And so probably the easiest way to do this is to multiply 3/7 by its reciprocal. Here, if I multiply 3/7 by 7/3, notice what happens. I'm able to cancel out the 7s, I'm able to cancel out the 3s, and I end up with exactly what I want, which is one of these things that are k, right? 1k. So this is another way of isolating the variable. Now, of course, if I multiply one side of the equation by 7/3, I need to do the same thing to the other side. And I say, oh my boy, I might need a calculator here, right? What's 12 times 7? Oh, it's 84 divided by 3. I don't know what that is, right? Well, I can also, because as we saw in an earlier problem, I can also rewrite 12 times 7/3. I could rewrite that, if I wanted to, as 12/3 times 7, right? As long as I'm keeping my numerators and denominators in the right place, I can sort of manipulate fractions in this way, and that's a little bit easier to solve because 12/3 is just 4 and 7 is 7, so I can say that altogether 1k equals 28, so that's my answer. My answer is k equals 28. So 3/7 of 28 equals 12. Great, let's keep going. Example number 5, you eat 2/3 of a pizza and then your dog Gnarly eats 2/5 of what was left. So what fraction of the original pizza is left? Gnarly looks very happy with himself. So let's start from you eating your pizza. So if you eat 2/3 of a pizza, the question we want to ask ourselves is what is left? Okay, well, if you start with one pizza and you take away, right, you eat 2/3, what's left? Well, 1/3 of the pizza is left, right? We can see this if I, instead of writing 1, we can see it more explicitly if I write 1 as 3/3, right? And so 3/3 minus 2/3 is just 1/3. So after you're done with the pizza, you have 1/3 left. Now Gnarly is going to eat 2/5 of that 1/3, okay? So again, we're going to ask ourselves the question, after Gnarly eats 2/5, what is left, right? What is left? And so if he eats 2/5, then, right, 3/5 of what he ate is left, okay? So 3/5 of the 1/3 that you left him is left. So altogether, what is left is 3/5 times 1/3, otherwise known as, I can cancel out my 3's, or I could multiply and divide, otherwise known as 1/5. So the answer to this question is 1/5 of the pizza is left. If I wanted to be a little more explicit and sort of put all of this into one equation, I could say that you eating 2/3 of the pizza means that 1 minus 2/3 of the pizza is left. Gnarly eating 2/5 of the pizza means that 1 minus 2/5 of the pizza is what he leaves. And so if I multiply this together, I end up with 1/5. Okay, so that's one way to sort of take these two parts right here and just put it into one simple expression, or equation in this case. Okay, so let's keep going. So we're almost done. You guys are doing great. So the think, pair, share here is asking us to take a look at this rule for dividing fractions that I'm sure we've memorized, or we may have memorized. So we flip and multiply, right? So that's how we divide fractions. If I have 2/3, right, divided by 8/6, I keep the 2/3. I take this thing, I flip it around so it's 6/8, and I multiply across and simplify, and I end up with my answer, right? So this is definitely a rule. It is something that we can memorize and we can use, and it will always work. The question we want to think about is why? Why does this rule work? So take a minute and see if you can sort of come up with some argument for why this rule works instead of another one, right? I could have made up another rule. Oh, you take the 3, and then you take the 8, and then you divide them, or you add 4 to them, right? There's a gazillion rules you could come up with. Why does this rule always work, right? So why does this rule always work? Okay, so let's take a look at it. So let's take a look at our example. We have our 2/3 divided by 8/6. So one way of sort of reasoning about this problem here is we really want to get rid of the denominator here, right? Because I want to end up with just one fraction, right? And the problem is now I have like a fraction here, I have a fraction here, the whole thing is a fraction, right? I really wish this denominator, 8/6, I wish it was just equal to 1, right? Because if it's equal to 1, anything divided by 1 is just that thing. So we can sort of like, you know, ignore it, essentially, right? So how can I get 8/6 to equal 1? Well, I can multiply by the reciprocal, right? I can multiply by 6/8, and just the same way that if we are multiplying by one thing on one side of an equation, we have to do the same to the other. In order to preserve the value of this expression right here, if I'm multiplying by 6/8 in the denominator, I will also need to multiply the numerator by 6/8. And look what happens. Magic happens, right? Because on the bottom here, I can cancel my 6's. I can cancel my 8's. Altogether, my denominator here is just equal to 1. Okay, so I'll just leave it there for now. And on the top, what do I have? I have my 6/8 times 2/3. Okay, and again, what I just said, right, was that anything divided by 1 is just the thing itself. So I can rewrite this as, I'm just going to flip the order in which I'm multiplying. I can do that, right? 2/3 times 6/8. And I'll be darned, that's our flip and multiply algorithm right there, right? So that's one way to sort of reason about it. When we're using this algorithm, this pattern of flipping and multiplying, really what we're doing is we're multiplying the numerator and denominator by the reciprocal of the denominator in order to turn it into 1 so we can just kind of ignore it, right? That's the big idea. Let's do one more problem. Example number 6. If a over b equals 2/5, then what is the value of b over a? Okay, great. So we can actually solve this problem without doing any work. All we need to do is flip the fraction, okay? So if a over b is equal to 2/5, b over a, this ratio, is equal to 5/2. Okay, just like that. We could, if we wanted to, try to solve it sort of by cross-multiplying. We'll get into that a little bit in the next lesson. I could write that 5a is equal to 2b if I cross-multiply, right? And then I could divide, right, both sides by a and by 2. I could divide both sides by a and by 2, and I end up on this side getting what I want, which is b over a, right? That's what we're being asked for. And over here, 5a divided by 2a is just equal to 5/2, right? The a's cancel. So this is one way that we could do it algebraically, but much nicer to just say, wait a minute, flip them, right? a over b, b over a, 2/5, 5/2. Great, thanks so much. Hope you enjoyed this, and stay safe.